So we've talked about errors, uncertainties caused by your equipment, and we've talked about uncertainties caused by systematic effects, things you haven't modelled. And you can never get rid of those. You can buy the most expensive equipment in the world and spend decades trying to nail down every possible systematic error, and there will always be more, but you can often do very, very well on that. But let's say you had perfect equipment, no uncertainty in that, and you got rid of every systematic error, you would still not be able to get perfect accuracy. There are a couple of very fundamental reasons why everything has an uncertainty. One of these is heat, thermal noise. For example, length of this ruler. You might think it has a particular fixed length, but of course it's made of atoms, and the atoms are not at the temperature of absolute zero, so they're all jiggling around. So if you had a really good microscope and you looked at the top, the length is always changing, it's going up and down. This turns out to be a real problem for electrical circuits. The actual voltage, you might think you've got a circuit with you 3 volts. What you'll actually find if you look with enough precision is the voltage is always changing and wobbling slightly around 3 volts because all the atoms and the electrons are wiggling around, and electron will get knocked one way by the thermal motions of the atom and knocked the other way. So in practice, any electrical circuit has a slight variation in the current and voltage just due to the heat. And it turns out this is a major problem. For example, when you tune a radio station, most of that static you pick up is actually amplified thermal noise. So you can make the static go away by cooling things down. So thermal noise is a big problem. It, for example, is what limits the gravity wave detectors at the moment. There is a way to fix that, which is to cool things down. If you could cool everything down to absolute zero, then you wouldn't have any thermal noise. You can't cool things to absolute zero, but you can make them very cool. And indeed, if you go around the labs here at the ANU, an awful lot of them, the equipment will be inside what's called a Dewar flask, or some sort of vacuum chamber, and will be cryogenically cooled. However, that's very expensive. It means you can't tinker with the equipment because it has to be in a cooled vacuum chamber. You have to pump liquid nitrogen or liquid helium or something around it the whole time. It's not feasible for day-to-day apparatus. But let's say you could bring things down very close to absolute zero so the thermal noise goes away. Even then, there is still more noise, which comes from the very fundamental nature of reality, from quantum mechanics. The theory of quantum mechanics, so most of the theories you've seen so far in physics tell you a different answer. If you use Newton's laws, it'll tell you the force is this, or the mass is this, or the acceleration is so and so. It gives you a definite number. Quantum mechanics doesn't do this. All it tells you is probabilities. It can tell you the probability that an electron is in a particular place as opposed to somewhere else. It can tell you the probability that the voltage has a particular value. But there's always some variation. This was very hard for the inventors of quantum mechanics to come up with. Einstein famously said, "God does not play dice." But it's now clear, God does play dice. There is a fundamental randomness at the limits of the world. Normally it's not a problem, but for the really sensitive experiments it is a problem. For example, quantum mechanics is what limits the sensitivity of the Large Hadron Collider. It's what limits the sensitivity of most modern telescopes. We're trying to measure how bright something is, so what we're trying to measure is the arrival rate of like photons per hour, which is often very low. It could be like 1 photon every 10 minutes. But that's a probability. If there's 1 photon supposed to arrive every 10 minutes, it doesn't mean every 10 minutes another photon, 10 minutes, another photon. It means there's a certain probability of a photon arriving in any given time. Sometimes 3 will arrive in quick succession, then nothing for a long time. So this fundamental randomness limits many observations. So, you can never, ever measure anything that's worth measuring precisely. There is always going to be an uncertainty from some sort or another. So we have to learn to come to terms with that.